Or some of the main ideas and formulas behind differential equations and 4 of the most important numerical methods for solving them: Taylor series, Euler method, Runge-Kutta fourth-order method, and predictor-corrector method. Let's start with the basics. A typical first-order ordinary differential equation has the form dy by dt equals f, a function of t and y, with an initial value y at t naught equals y naught. This defines how y changes with respect to time. To approximate or analyze solutions, we sometimes expand functions using a Taylor series. About x equals a, the expansion of f(x) is f of a plus f prime of a times x minus a, plus f double prime of a over 2 factorial times x minus a squared, plus higher order terms. Let's move to the Euler method, one of the simplest ways to numerically solve an ordinary differential equation. The Euler update says that u sub k plus 1 equals u sub k plus f of t sub k, and u sub k times delta t, where t sub k equals t naught plus k times delta t, and u naught equals y naught. This means take your current value, add the slope times your time step, and that gives you the next value. Let's visualize this idea. Imagine the slope of a curve at some initial point. The Euler method takes a small step along that slope. We'll visualize that as a small line segment, which becomes our new y value, then repeat. The smaller the step size delta t, the better the approximation. Euler's method is only first-order accurate, which means errors can build up. A much better approach is the Runge-Kutta method of order 4. The RK4 step calculates 4 slopes, averages them in a weighted way, and produces an update formula that is much more accurate. Here's the formula. To picture what Runge-Kutta is doing, think of it as sampling the slope at different trial points between t sub k and t sub k plus 1, combining them to get a good prediction for the next point. Another approach is the predictor-corrector method. One of the simplest and most common is called Hume's method. First, make a prediction for the next value using Euler's update. Then, make a correction by averaging the slope at the previous and predicted points. Here is the step-by-step formula.